Dr. Kirti is working as Assistant Professor in the Department of Chemistry, Anna University, Chennai. She finished her UG and PG from Government Victoria College, Palakkad. She completed her MPhil from Loyola College, Chennai with gold medal and PhD from Anna University. Her main areas of research area are membrane technology in wastewater treatment and nanocomposites for energy application. She has published more than 12 papers in national and international peer-reviewed journals of high repute. She has presented more than 5 papers in international and national conference. She has received research projects from DST for more than 43 lakhs under Women Scientist Scheme and Technology System Development. She has 6 years of experience in research and teaching in chemistry, polymer science and environmental science.
Welcome to UGC lecture series on polymer science. Today we would be dealing with atomic and molecular spectroscopy. In the last class we have seen what spectroscopy is, how electromagnetic radiation interacts with matter, and that process is known as spectroscopy. Now in this lecture you should know what is atomic spectroscopy and what is molecular spectroscopy. So in this lecture the contents are: the energy levels in an atoms will be discussed, the different energy levels in a molecules will be discussed using Jablonski diagram. In Jablonski diagram we would be seeing different emission processes such as non-radiative emission processes and radiation processes. So with this we should be knowing what is the basic difference between atomic spectroscopy and molecular spectroscopy. So these are the contents. Let's go ahead. The first topic is energy levels in atoms. As in the last lecture I have told you, there are different energy levels in a molecule, that is electronic energy levels, vibrational energy levels as well as rotational energy levels. But in the case of atoms we will not have vibrational energy levels and rotational energy levels. In the case of atoms it will be only electronic energy levels as seen in this slide. You can see in the slide we have only electronic energy levels. The ground energy level is described by S0, which is known as the ground electronic energy level. The excited energy level is designated by S1, and the higher energy levels are designated by S2. Now the energy difference between these two energy levels, let it be the ground energy level and the excited level, or from this first excited level to the next excited level, that is S2, it is designated by delta E. Now the relative population of electrons in these energy levels is given by the equation n upper by n lower is equal to exponential of minus delta E by kT. Let me repeat this. The equation, the relative distribution of electrons in these excited energy levels is given by the equation n upper by n lower, where n upper is the number of electrons in the excited level, n lower is the number of electrons in the ground state, is equal to the exponential of minus delta E by kT, where delta E is the energy difference between the upper energy level and the lower energy level. That means delta is the energy difference between the excited energy level and the ground state of electronic energy. K is known as the Maxwell-Boltzmann constant, which you are very well aware of, and T is the absolute temperature. So this equation defines the relative distribution of electrons at a particular temperature and is given by the equation exponential minus delta E divided by kT. As I have told you, K is the Maxwell-Boltzmann constant, T is the temperature, delta E is the energy difference. Now in the last lecture you should be remembering delta E is equal to h nu, where h is the Planck's constant and nu is the frequency of the radiation. So therefore this equation can be rewritten as exponential of minus h nu by kT, where delta E is equal to minus h nu, that we have seen in the last lecture, where h is the Planck's constant and nu is the frequency. So, this is the simplified energy level diagram of an atom and the interaction with electromagnetic radiation resulting in absorption and emission of radiation. Now, you can see here there is, if the atom absorbs energy from electromagnetic radiation, it absorbs energy and gets excited from the ground energy level to the higher energy level. You can see here when the electrons gets excited from S0 level to S1 after the absorption of electromagnetic radiation, that process is known as absorption and is denoted by the letter A. Now, after some time, these excited electrons relax back to the lower electronic energy levels, and that process is known as emission and is denoted by the letter E. So, these are the two different processes in atomic spectroscopy, that is, the electrons from the ground energy levels can get excited to higher energy levels by the absorption of energy, and it is known as absorption. Whereas, when the electrons are excited, after a lapse of time, the electrons can get de-excited to the lower energy levels or the ground energy levels, giving away emission of radiations. So, that process is known as emission. So, in the case of atomic spectroscopy, these are the two basic processes that takes place in the atoms, that is absorption of energy by absorption of electromagnetic radiation and emission of radiation by giving away the radiation when it comes back to the ground energy level. So, these are the two basic processes that happens in atomic spectroscopy, and accordingly it is known as atomic absorption spectroscopy, where there is absorption of energy and the electrons gets excited from the ground energy level to the excited energy level, and atomic emission spectroscopy, where the electrons in an atoms get de-excited, giving away the emission of radiation, and it goes to the ground energy level, and that process or that kind of spectroscopy is known as atomic emission spectroscopy. So, by this slide I hope you have understood what are the different energy levels in atoms. Atoms contains only electronic energy levels, and these are two processes, that is atomic absorption spectroscopy and atomic emission spectroscopy, which takes place in atoms. So, this is the energy levels in atoms. Before going to the molecular energy levels, there are certain things or terminologies that you should know, and that is known as singlet and triplet states. Now, let me tell you, in the case of molecular energy levels, the ground state is when the two electrons per orbitals have opposite spin and paired. So, in the ground state of molecules, the two electrons in the orbital will have opposite spin and they will be paired. And you should also know the process known as spin multiplicity, which is nothing but the equation is given by 2s plus 1, where s is the resultant spin. So, in the ground state, as we all know, the electrons per orbital will be in the paired situation. So, they will have opposite spins, and you should also know what is spin multiplicity, which is nothing but 2s plus 1, where s is equal to the resultant spin. Now, resultant spin is nothing but S1 plus S2, where S1 is the spin of one electron and S2 is the spin of the other electron. So, in the ground state, as you can see in this figure, this is the ground state of an electron pair. You can see here that the electrons are paired. That means this electron will have a spin of plus half, whereas this electron will have a spin of minus half. So, if we see the resultant spin, that would be equal to plus half plus minus half, which is equal to 0. Now, you have to understand, in the ground energy state, the electrons are paired. That is, one electron will have plus half sign, whereas the another electron will have minus half sign. So, the resultant spin, that is S, is equal to S1 plus S2. So, S1 is plus half plus minus half. So, plus half and minus half gets cancelled and the resultant spin is S is equal to 0. Now, when you apply this in this equation 2s plus 1, you will see that S is equal to 0 that we have derived, that is the resultant spin of the ground level is 0. So, therefore, spin multiplicity 2s plus 1 is equal to 1. So, in this case in the ground energy level, that is what we see, that the ground energy level is given as singlet. So, the ground state of the molecular energy levels, the ground state is denoted by S. That means it has a singlet state which is spin multiplicity is equal to 1. So, that is known as singlet state. In the case of excited states, we have two different orientation and accordingly it is denoted as singlet states and triplet states. Let us see how this happens. Now, in the case of singlet excited state, the electrons in higher energy orbitals has the opposite spin orientation relative to the electron in the lower orbital. Let me explain once again. Electron in the higher energy orbital has the opposite spin orientation relative to electron in the lower orbital. Now, you can see in this diagram, this is the ground energy level where the electrons are paired. That means, this electron has opposite plus half sign and this electron have minus half sign. When this absorbs energy and gets excited, you can see that still the electron in the lower energy level have plus half sign, whereas this minus half of spin of the electron is retained in the excited level. Here also, if we keep this as S1 and this as S2, the resultant spin S is equal to minus half, or we can say this has plus half plus of this minus half. Now, the resultant spin is again 0. Even when the electrons are excited to higher energy level, it retains its spin to minus half. Therefore, the resultant spin is again 0. So, therefore, the spin multiplicity, if you calculate using the equation 2s plus 1 where s is equal to 0, you will get again the value 1. That means, the spin multiplicity is 1. Even though the electrons have been excited to higher energy level, the spin has been maintained. So, therefore, the resultant spin is 0 and the spin multiplicity is 1. Therefore, this is known as excited singlet state because the multiplicity S is equal to 1. Now, we have another case that we can see in the next slide. Now, there is one more state which is known as triplet excited state, where the excited valence electron may spontaneously reverse its spin, or it can undergo spin flipping. That means, it flips its spin. This process is also known as intersystem crossing, and the electrons in both orbitals now have the same spin orientation. Let me explain this once again. The excited valence electron may spontaneously reverse its spin. That means, it undergoes a flipping in the spin. This process is known as intersystem crossing, and the electrons in both orbitals now have the same spin orientation as you can see in this diagram. Now, as we said, this is the ground electronic energy level where the spins are paired. That means, this electrons have a plus half sign and this have minus half sign. Now, when this electrons undergo absorption of energy, the plus half sign of the electrons when gets excited will undergo and it gets converted into minus half. That means, it undergoes a flipping of spin. So, here you can see that the electrons are not paired, it does not retain the same spin, but it undergoes a change in the spin, and that process is known as spin flip. Now, here you can see, if we consider this spin as plus half and this spin also as plus half, the resultant spin S is equal to plus half plus half. So, resultant spin will be equal to 1. Let me again tell you, since the spin is plus half in the lower energy level and plus half in the excited energy level, the resultant spin will be equal to plus half plus half. so which is equal to 1. Now, when you put this value into spin multiplicity equation, which is equal to 2s plus 1. So, 2 into 1 plus 1, the value will be 3. So, therefore, this excited energy level is known as triplet state. In the first case, the spin multiplicity S was equal to 1, therefore, it is known as singlet excited state. In this case, the spin multiplicity is equal to 3, therefore, this excited state is known as triplet state. So, these are the different excited states which occurs in a molecule. The ground energy level is always equal to singlet state, which is because its spin multiplicity is equal to 1 and the resultant spin is 0 since the electrons are paired. So, the ground energy level are singlets. We have two types of excited states, which is singlet excited state and the triplet excited state. So, as I have explained you in the before slides, this is just the representation of spin orientations in different energy states of a molecule. As I have told you, in a ground state, the electrons are paired, it will have a plus half sign and a minus half sign. When it gets excited, it can get excited into two states, one is the excited singlet state and the other is the excited triplet state, which I have explained you well by using the case of spin multiplicity, which is equal to 2s plus 1, where s is the resultant spin. Now, using this, we have to undergo or we have to understand what are the different energy levels in a molecule. As I have told you, in electronic energy levels in an atoms, in the case of molecules we have three kinds of energy levels. One is the electronic energy level, the other is the vibrational energy level and the other is the rotational energy level. So, that is the basic difference between the energy levels in a molecule and the energy levels in an atom. In the case of an atom, there are only electronic energy levels, they do not have vibrational energy levels and rotational energy levels, whereas in the case of molecules, you have all these three energy levels. That is electronic energy levels, which is greater than the vibrational energy levels and which is again greater than the rotational energy levels, which we have seen in the last lecture. So, using all these, we have different kinds of absorption processes and emission processes taking place in a molecule, which can be well explained in a diagram which is known as Jablonski diagram, which you see now. Now, here you can see that this diagram is known as Jablonski diagram, which represents the electronic, vibrational and rotational energy levels in a molecule. Now, in this slide you can see the different energy levels in a molecule, which is described by Jablonski diagram. Now, here you can see the electronic, vibrational and rotational energy levels in a molecule is shown. Now, here you can see this is S0. Now, I have told you that the ground energy level is denoted by S, that means it is a singlet state. Now, and this you can see it is denoted by S1, that means it is an excited singlet state. And now, here there is another again an excited state, which is again a singlet state. So, here you can see three electronic energy levels, that is the ground electronic level, which is denoted by S0, the excited singlet state, which is denoted by S1, and again a singlet excited state, which is denoted by S2. So, these lines are electronic energy levels. Now, you can see here, you can see there are again different lines which are very closely packed. These are given by the vibrational energy levels. That means, these lines will be denoted by the vibrational energy levels. Now, again you can see here the dotted lines are given by the rotational energy levels. Let me tell you once again, the dotted lines are given by rotational energy levels. So, in this diagram you can see three kinds of energy levels: the electronic energy levels, the vibrational energy levels, and the dotted line is given by rotational energy levels. In the last lecture, I have told you that the electronic energy levels are greater than the vibrational energy levels, which are again greater than the rotational energy levels. So, now in this Jablonski diagram you can see the electronic energy levels are greater than the vibrational energy levels, and the vibrational energy levels are again greater than the rotational energy levels. So, in this diagram you have seen singlet ground state, excited singlet states and another excited singlet states. Now, in this part of the diagram you can see a triplet state, that is, it is an excited electronic triplet state energy level, which we have discussed in the last slide, how the triplet state comes. That is, the electrons undergo spin flipping. So, they have the same spin, the resultant spin would be 1 and the spin multiplicity would be T. Now, here in this diagrams you would be wondering why the T1 state is less than the first excited singlet state. Now, you can see that the first excited singlet state have higher energy value than the first excited triplet state. That is because when there is an electron spin flipping, it uses some of its energy for the spin flipping. Therefore, the triplet state will have less energy level than the first excited singlet state. Let me tell you once again, when there is a spin flipping, some of the energy is used up for the spin flipping. So, therefore, in the first excited singlet state would be of higher energy, whereas the first excited triplet state would be of lower energy. So, here in this diagram you can see this is the first excited triplet state and this is the first excited singlet state and this is the second excited singlet state in the electronic energy levels. Now, in this diagram you can see different denotions, which is IC, VR and ISC. Let me tell you in brief what IC is. IC is known as internal conversion, VR is known as vibrational relaxation, ISC is known as inter-system crossing, F is known as fluorescence and P is known as phosphorescence. Now, in this diagram you can see all the emission processes are described by these denotions. Now, in this diagram you can see the emission processes are denoted by IC, ISC, VR, phosphorescence and fluorescence. IC is internal conversion, ISC is intersystem crossing and VR is vibrational relaxation. Now, emissions in this process in molecules can take place in two ways. First one is radiative emissions and the second type is non-radiative emissions. Let me tell you once again, in the emissions in molecules it can take place in two ways. First one is known as radiative emissions and the second one is known as non-radiative emissions. Radiative emissions is nothing but when the electrons de-excites from the higher energy levels to lower energy levels, the emission of radiation takes place. Let me tell you once again, when the electrons gets de-excited from the higher energy level to the ground energy levels, there is an emission of radiations. So, that is known as radiative emissions. Whereas, in the case of non-radiative emissions, when the electrons gets de-excited from the higher energy levels to the lower energy levels, there is no emission of the radiation, whereas it just the energy which is emitted gets converted into heat. There is no emission of radiation, there is only conversion of that energy into heat, that is known as non-radiative emissions. So, in the emissions taking place in a molecule, let me tell you once again, there are two types of emissions, radiative emissions and non-radiative emissions. Now, the radiative emissions are of two types, one is phosphorescence and the other is known as fluorescence, which you must be well aware of, or at least you could have heard of these names. The two types of radiative emissions are phosphorescence and fluorescence, whereas internal conversion, vibrational relaxation and intersystem crossings are types of non-radiative emissions. I hope you have understood two types of emissions, radiative emissions which are fluorescence and phosphorescence, whereas non-radiative emissions are intersystem crossing, internal conversions and vibrational relaxation, as you can see in the Jablonski diagram. Here you can see when the electrons gets de-excited from the higher excited singlet states to the lower rotational energy levels, it is known as intersystem crossing, or it can get converted from the higher energy levels to lower vibrational energy levels, then it is known as internal conversion. That means when the electrons gets de-excited from the highest excited energy singlet level to lower rotational energy levels, it is known as internal conversions. When the electrons gets de-excited from the higher vibrational energy levels to lower vibrational energy levels, it is known as vibrational relaxation. And when the electrons gets converted from the higher singlet state, when it gets converted to triplet state, this is known as intersystem crossing. All these three processes are non-radiative emissions, and it does not emit any radiation, the energy is just converted into heat. Now, in the case of radiative emissions, there are two types, phosphorescence and fluorescence. Now, in the diagram you can see that when the electrons gets de-excited from the higher singlet energy level to lower ground state electronic energy level, the process is known as fluorescence, where there is an emission of radiations. Whereas, when from the first excited triplet state, when it relaxes to the ground state electronic energy level, that process is known as phosphorescence, and these are the two radiative emissions which undergoes emission of radiation when it takes place. So, with this Jablonski diagram, you should know what are the different energy levels in a molecule, how the molecules absorbs energy and goes to higher energy levels, and how it relaxes in different ways to the ground electronic energy levels. The emissions are of two types, radiative emissions and non-radiative emissions, which is radiative emissions are phosphorescence and fluorescence, whereas the non-radiative emissions are internal conversion, intersystem crossing and vibrational relaxation. So, as I have told you, fluorescence is nothing but the return from excited singlet state to ground state. It does not require any change in the spin orientation, and it is the most common way of relaxation. And phosphorescence is the return from a triplet excited state to a ground state, where the electron requires a change in the spin orientation, which I have explained to you very well. Now, you can see that the emissive rates of fluorescence are several orders higher in magnitude than that of phosphorescence, because phosphorescence requires a change in the spin orientation, whereas in the case of fluorescence there is no requirement of spin changing. So, in the case of fluorescence, it is the most common way of relaxation, whereas phosphorescence is rare and it is slow in magnitude because of its change in the spin orientation. Now, the two different kinds of non-radiative emissions which I have told you is the internal conversion, which occurs when a vibrational state of an electronically excited state can couple to a vibrational state of a lower electronic state, whereas intersystem crossing is a transition to a state with a different spin multiplicity, which you have seen in this diagram, that there is a change in the spin multiplicity from the singlet state to the triplet state. So, in this case there is a transition in the spin orientation and it is known as intersystem crossing. So, now if you see at this slide, we have been telling you there is two types of spectra, absorption spectra and emission spectra. Now, in this figure you can see this is the detector output versus frequency. The spectrum of an atom or a molecule undergoing a single transition. The ideal spectrum would be of line type, whereas the actual appearance you can see there is a broadening in the peak which happens due to various processes which we will be taking into account in the next lectures. So, let me summarize this lecture. With this lecture, you should know what are the different energy levels in an atoms and molecules. So, therefore, you should know what is the difference between atomic and molecular spectroscopy. The electronic energy levels in a molecule was described using Jablonski diagram, where you know what are the two types of different emissions, non-radiative emissions and radiative emissions, and you should know how an actual spectra looks like, where we think that it should be a line spectra, whereas the spectra is usually we have a broadened peak. In the next lecture, we would be seeing what are the different reasons for the broadening in the line spectra, why the spectras are broadened, which we would be dealing with in the next lecture. With this lecture, you should be able to answer these questions. What is the basic difference between atomic and molecular spectroscopy? Describe the energy levels in a molecule using Jablonski diagram. List the differences between phosphorescence and fluorescence. So, with this lecture, you should be able to answer all these questions. Thank you.